Hello everyone, welcome to MatSQ 110 webinar. Thank you for joining today. I'm Min-Kyu Park, in charge of Chief Scientific Officer of Virtual Lab. So today we invite a special guest, 𝗙𝗁 Lee. He is currently working on the Korean Institute of Science and Technology in the group of the Computational Science Research Center as a senior researcher, and he has studied on density functional theories. So today he will be going to give a talk about understanding electronic structure of Halide Perovskite first principle calculations.
Okay, hello guys. I'm 𝗙𝗁 Lee from KISS. I'm happy to give a talk in this webinar organized by Virtual Lab. Also, I'm happy to see you guys. I see that you guys from Iraq, South Korea, Brazil, Slovakia, India, what else? Pakistan, right? Okay, good to see you guys. So today I mostly talk about the what is the first principle and DFT calculations. Let me share my screen first. Okay. I guess you guys can see my slide now. Yeah, I mostly talk about what is the first principle and DFT calculations, and I will show you some applications for halide perovskite materials, and we will do some tutorial practice. So let us begin with the basic concepts of DFT calculations. So DFT is the one of first principle calculations. So first principle or ab initio is the same word actually. So ab initio is a Latin term which means from the beginning. So ab initio calculation or first principle calculations, we don't need any assumption or empirical parameters. So this is the solving very fundamental equations such as the Schrödinger equation. So Professor Robert Park from the University of North Carolina at Chapel Hill, he firstly used the ab initio word in his JCP paper in 1950. So in this paper, he was like the computations which are heavy will carry through independently ab initio. So he firstly used ab initio. Yeah, as I mentioned earlier, density functional theory, normally we call DFT, is one of ab initio methods. Let me, okay. So, yeah, so doing ab initio or first principle calculation is just solving a fundamental equation here, Schrödinger equation. So this is the well-known, you guys already know that this one. What is this? This is the Schrödinger equation. The Hamiltonian is composed of kinetic energy here and potential energy here. And this is the state of electrons and total energy and the electron gain. So the DFT is one of methods to solve this Schrödinger equation. So there are many ab initio methods such as the Hartree-Fock and coupled cluster and DFT. So I would say DFT is the most efficient and an accurate method to solve this Schrödinger equation. So also most widely used method. Okay. So for hydrogen atoms, we can exactly solve the Schrödinger equation because there is only one electron and neutron. So we just need to consider wave functions for electron. So it's easy. Also, you may remember that we did some homework, to solve the Schrödinger equation manually, right? So it's easy. But what about the other systems like solid? So for example, silicon is most widely kind of benchmarking material for DFT calculations. So we know that there are two atoms in the primitive cell. So since the one silicon has 14 electrons, there are 28 electrons in the primitive cell. Then to solve this system, we have to like consider so many configurations. So this is massive. This becomes a very massive calculation, and practically, well, if you have a just laptop or desktop, it's gonna be very challenging calculation because it's very massive calculation. So we need to do kind of develop some efficient method or use the other way to solve the Schrödinger equation. Okay, so this is the very important concept in DFT calculation. So we basically use the electron density instead of the electron wave function. So this blue line corresponds to the electron wave function. So the left one is electron density, which is defined by this one, the scale of electron wave function. So now the basic variable is electron density, not the wave function. So the basic variable is not electron density. So it should be much faster. Also, this electron density already include the all informations what we need in calculation. So it is likely to be accurate. So this is key concept of DFT. And then you might think that what is the functional, not function. So functional is totally different from function, just function. We know that function input is a variable and output is input is value, sorry, and output must be value too. But in functional, input is the function, not the value. So in DFT calculation, input is the electron density, not the electron. So output is the value. So this is the functional. So input is a function and output is value. So that's why we call density functional. So yeah, using this concept, the energy here, energy means total energy, can be written in terms of electron density. So if we know the kinetic energy operator as function of electron density and potential energy operator as function of electron density, when we sandwich this Hamiltonian, we get the total energy as function of the electron density. So this is much efficient way to solve the Schrödinger equation. So actually, the 𝗏𝗏𝗃𝗀𝗃 theorem is sort of a starting point of DFT calculation. So this theorem tells us that the ground state electron density here, N0, uniquely determine the external potential here. So the other word, external potential is uniquely determined by electron density. And second, the electron density then minimizes the total energy. E is the exactly ground state electron density. So that means if we know the ground state electron density, then we can get the all informations what we need. So here electron density is important. So doing DFT calculation is actually finding ground state electron density. So you may think about this way. And there are some approximations. The first one is a mean field approximation. Basically, to accurately describe the electron many-body interactions, we have to like consider all interactions using this Coulomb interaction. But in DFT calculations, we basically replace this many-body interactions with the average potential, something like this. So one electron just feels, a potential from the electron density, not the many bodies. So equation is something like this. So electron density over distance between two, how can I say, between the electron density. So this is called the mean field approximation. So average field potential. And second one is the Born-Oppenheimer approximations. You guys already know this concept. Since the nuclei nuclear is about 2,000 times heavier than electron, we, kind of ignore the nuclear movement, just consider a electron movement while fixing the position of a nuclei. And yeah, using these concepts and some approximations, Professor Walter Cohn from UC Santa Barbara, and let's move my face, and Professor Lu Xiang from UC San Diego created this Schrödinger-like equation, which is called the 𝗏𝗁 equation. So basically, it looks like the Schrödinger equation. So this is kinetic potential, but potential looks a bit different from Schrödinger equation because this potential is composed of external potential, which is the potential for nuclei electrons. And second one is Hartree potential, which is electron-electron Coulomb interactions. This one is correspond. Okay. Oh, oops. What happened? Somehow my computer becomes very slow. Yeah, it corresponds to this interaction, Hartree. And last one is exchange correlation potential. This is very mysterious potential. Anyway, they kind of made this Schrödinger-like 𝗏𝗁 equation. So DFT calculations, actually doing DFT calculations is solving this 𝗏𝗁 equation. So let me explain the exchange correlation potential first. So this exchange correlation interactions are purely quantum mechanical effect. So this and this exchange correlation energy actually is divided into two parts. The first one is exchange energy. So this is very similar to the Pauli exclusion principle. So basically, two fermions cannot occupy the same spatial and spin state. So it's basically similar to the Pauli exclusion principle. So yeah. So this is possible configuration, but I don't know why my computer is very slow. Anyway, this is unlikely to happen. Yeah, because it's energetically this is very unstable. And the second one is more complicated. The correlation effect. So let's think about this way. So one electron is moving like this in the some electron reservoir or just electron density. Then this motion basically is related to the motion or position of the other electrons in this electron density. So there is very complicated interactions between electron and the other electrons. So this is some pictorial and schematic view of exchange correlation interactions. So let's say there are two electrons in the electron density. So this gray region is the electron density, and there are two electrons. And let's think about some possibility to find these two electrons near here. But according to the exchange correlation interactions, the possibility close to the zero here because of exchange correlation interactions. Then this region is then becomes like electron depletion region because there shouldn't be electrons here. So if we if you do some integral over this region for electron density, and this becomes -1, so that means that this region is positively charged. So this is the famous exchange correlation hole. So there is a hole. Okay, then this electron and this electron density, there is some interaction here. So this is exchange correlation interaction. So it's technically or the numerically it's really hard to describe this exchange correlation functional. So normally we just approximate these interactions using some different functionals like LDA. You may hear about these functionals: LDA, GGA, meta-GGA, and hybrid functionals. So these are also very important to get a very accurate result. But I'm not gonna talk about these guys in detail this session. Anyway, well, if you maybe look at these words in the paper, and you may think, oh, these guys are exchange correlation functional, and this is approximations for electron behavior. So lastly, I like to talk about the pseudo potential. So normally in every DFT calculations, we use the pseudo potential, not the exact original potential. So pseudo potential is we basically modify the original potential. So this is the original electron wave function. And let's say this one is external potential generated by a nucleus here, nuclear here. So but we know that this core electrons never influences electronic structure of materials, because the valence electrons play a key role in the fundamental properties of material. So we just kind of modify this core part with very smooth wave function. So to describe this short wavelength region, we need many bases. That means our computation time increases. But by smoothing this core part, the calculation become very faster, and also with guaranteeing accuracy. So the pseudo potential is also very important kind of a technique in DFT calculations. So this is the flow chart for DFT calculations. Again, I like to say doing DFT calculation is solving 𝗏 equations. So let's follow this flow chart. Initially, we need initial gas, something like electron density. Then we can calculate the potential and kinetic energy too. Then output electron density can be obtained from the wave function here. Then we will compare this output wave function and initial wave function. Then if these two guys are the same within some criterion, then calculation is finished. And after calculations, we get the energy, force, stress tensors, eigenvalues, and the other properties of material. So this is how DFT is working here. So here there are many DFT codes like Quantum Espresso, Siesta, 𝗙𝗵𝗃, 𝗏𝗏𝗃, BASP. All are very good codes. I'm personally have been using Quantum Espresso, Siesta, and BASP. And Quantum Espresso is quite nice. This is free, easy to install. Siesta is also very nice, very fast. 𝗙𝗵𝗃 is quite good and free too. These three guys are free. And 𝗏𝗏𝗃 is only free for UK academia, as far as I know. But 𝗏𝗏𝗃 also, 𝗏𝗏𝗃 and BASP, they look like very similar. And BASP is kind of a global standard DFT code, but it's not free. So if you have a budget, you can just buy this BASP code. But if not, I would go Quantum Espresso or Siesta, because their forums and communities are very big. So yeah, because of this contribution, Professor Walter Kohn got Nobel Prize in Chemistry, 1998. So, but he passed away 5 years ago. I remember I was really sad with his death because he's a kind of really big guy in DFT community. So these would be input for DFT calculations. You guys have to provide your system, such as the lattice parameters, atomic positions, and atomic types, or which atoms you are looking at, and you also have to choose the calculation mode. So if you want to get some optimized lattice and atomic positions, you kind of can choose this mode. And if you just only need a optimized atomic positions, you can choose this one. Or sometimes we just need a optimize the electron density. So, and also we need some convergence criteria and electronic and some input parameters for some reciprocal space like 𝗙 and electron smearing things. So, but you don't need to worry about this because I guess the material scale platform already provides some default very nice and how can I say it's very reasonable input parameters. Okay, and let's look at some applications of DFT calculations on the Halide Perovskite materials, because I have been looking at the Halide Perovskite materials using DFT calculations since maybe 2014 or 15. So maybe some of you guys are familiar with this solar cell efficient chart. This chart is from the NREL website. So if you look at these yellow points, the yellow points corresponds to the solar efficiency of Halide Perovskite solar cell, and this blue point is a silicon solar cell efficiency. So this efficiency is almost approaches to the silicon solar cell efficiency. It's almost same now. So this is really good. Also, this is really much cheaper than silicon solar cell. So we can say why not? And this is the very promising candidate for future solar material. And the reason why they show the good properties is that it is show very this has a long carrier diffusion length, something like this. It's very long. The carrier can survive very long, you know. Also, this material has a really good bandgap. So this one is a theoretical maximum solar cell efficiency as function of the bandgap. So this blue dot corresponds to the Halide Perovskite material. So bandgap and efficiency is almost close to the theoretical maximum efficiency. So this is really good. Also, this can be flexible in this, big scale. So we could think about the, flexible solar cells and many applications in some curve shape. So this is quite nice. Also, recently, Stanford team developed a new technique for large area perovskite solar cell. So they basically can make the 12-meter solar cell per minute with a very cheap and relatively high efficiency. So let's look at some video here. So you see it's just, takes the maybe 2 seconds or 3 seconds. So this is really amazing. And there are also transparent perovskite solar cell, which is made by a Polish company, 𝗙𝗶𝗿𝗀𝗀𝗀. So this is also very nice. But there are still some problems need to solve stability and toxicity issues. Like if there is waters and water can, destroy this material and decompose, into some two phases. So this is really bad. So water stability is really bad. And sorry. Also, since there is a lead atom, so this is toxic. So these lead atoms can kill our human cells. So we have to replace these lead atoms with the other non-toxic elements. Well, nevertheless, I feel like the commercialization is just around the corner, because so one company which is called 𝗙𝗶𝗿𝗀𝗶𝗃, this is the spin-off company from the Oxford University. They actually developed the large-scale perovskite solar cell on the silicon substrate, and they indeed are selling this solar panel. So since they solved some stability issues and other stability issues here. Also, many researchers have been extensively studied the lead-free perovskite, such as this material. So my collaborator, Professor 𝗙𝗹𝗰𝗂𝗀𝗃, actually synthesized this material by, replacing lead atoms with non-toxic silver and bismuth atoms, and they also can tune the band structure and optical properties. So this is the yeah. So I hope these materials can replace the modern material, including lead atoms. Okay. Okay, and then I will show you some my DFT results for different applications. First of all, using DFT calculations, we optimize our structures, something like this, and can look at some chemical bondings here and here. Oh, okay, there is some hydrogen interactions here, and we could understand some chemical nature inside materials. Also, we can easily get the band structure of the materials, and we can also get like some effective mass and what is band gap, where is the band gap, and lastly, not lastly, sorry, and also we can get the density of state of material. So we from the density of state, we could understand some orbital interactions and other electronic structure properties. So today we're gonna do some optimize our example structure. Also, we will look at the band structure of the some representative halide perovskite material. We're gonna look at these two properties today. Also, using DFT calculations, we can easily get the mechanical properties. These are Young's modulus of the halide perovskite on the this is directional dependent Young's modulus on the each planes. And basically, we use the electron density, so we get some wave function. So you can see some orbital interactions too. So these are applications, and let's move on to tutorial sessions. But before doing some practice, I will briefly explain how can we use the our tutorial platform, MaterialScale. So basically, we will look at this halide perovskite material, cesium lead iodide. So firstly, we're gonna optimize our structure. So in DFT calculations, to optimize our structure, we use the 𝗙𝗻𝗰𝗃𝗀𝗃 theorem. This is the 𝗙𝗻𝗰𝗃𝗀𝗃 theorem. So this theorem tells us that the total energy, the derivative of total energy with respect to some variable, here variable is the displacement of atoms, is equal to the expectation value of derivative of Hamiltonian with respect to the variable. So this is 𝗙𝗻𝗰𝗃𝗀𝗃 theorem. Then this one becomes a force. Then we get the force is equal to this one. So this is very interesting result because there is an electron density here. The force is determined by electron density, which is the really different from the classical mechanics. This is a purely quantum mechanical effect. So this gives us really interesting message, which is that quantum mechanical force arises from total electric field, which is generated by nuclei also, as well as the electron charge distribution. So electrons really is really acting on the nuclei. So this is very interesting point in the structure optimizations in DFT calculations. So okay, so this is flow chart. We provide atomic positions first, and then DFT will calculate the electron density and total energy, and using Hellman-Feynman forces, we could compare the calculated one and the initial one and compare that. And if the positions are the same and calculation is finished, but otherwise go to the first step, iteratively DFT optimize the force tensors. And for the electronic structures, we have to know what is the reciprocal space and reciprocal lattices. So, well, I guess most of you you guys know the what is the reciprocal space. This is the Fourier transform or real space. So, well, when I was an undergrad student, I was like, why we need a reciprocal space? Because we know the real space structures, but there is something meaning. Yeah, but there's this is still meaningful because the using a reciprocal space concept or K-space K-space concept, we can easily calculate the quantum state numerically and technically, because a quantum state is defined by a K and G. The K is the good quantum number, which is defined in the reciprocal space. So that's why we need a reciprocal space. Also, G is the reciprocal lattice vector. So the reason why we use the wave function is that using wave functions, we can numerically easily and numerically calculate the quantum state and eigenvalues. So because of that reason, we need a reciprocal space and quantum reciprocal lattices. Also, there is some physical meaning. So K is a good quantum number. So to understand the electronic structure, we have to define some variable in energy space, which is K, quantum number. So we know that reciprocal lattices is inversely proportional to the real space lattices. So yeah, this A1, A2 are real space lattices. Well, if you do some, if you look at the reciprocal lattices of these two guys, and these B1 and B2 are the reciprocal lattices. And from here to here, the angle is, from 120 to the 60 degrees. So because the reciprocal lattices are basically inversely proportional to the real space lattices. Okay, so Brilliant also we need to know what is the Brilliant zone. Brilliant zone is the primitive reciprocal lattice cell, so which is similar to the unit cell in real space. So you could think that you can regard this Brilliant zone as the unit cell in the reciprocal space. So to get the eigenvalues at given k point, we have to solve the this Schrödinger equation at given k points in this Brilliant zone. So calculating eigenvalues at given k point in the Brilliant zone means that understanding electronic structure of a periodic material system. So from M to R, we calculate the eigenvalues at given k point, and from R to gamma, also we get the eigenvalues at given k point. So to get these eigenvalues at given k points, we have to adapt the this reciprocal space and Boolean zone in our calculation. Okay, let me briefly explain how to do this tutorial. Initially, you need to go this material scale web page. I guess you already in this web page. This is web-based platform, cloud computing. They provide a professional consulting technical support, and we use Quantum Espresso for our DFT calculations. So let's show you how to optimize structure. Initially, you have to log in first, go to the work, and add your new work here, and drag or upload your crystal structure. I guess you guys already have a structure. And then check your structure, and go to simulation, DFT Quantum Espresso General, and then connecting your structure into your Quantum Espresso. And yes, check your info files and changing your scripting option to general. Okay, then calculation type is BC relax. BC means variables are relaxed because we're gonna relax our unit cell. And K points, you have to change K points. Yeah, now it's 111, but we should use the large K point because the as I mentioned earlier, reciprocal lattice is inversely proportional to real space lattice. So let's say, for example, 10 by 10 by 10 cell, you may need a 444, but for 666, you need a more K points because this is inversely proportional. What about 864? And this case, you can choose like 468. So our case, I use the 666. Also, there is the interesting option which is a shift. So using this shift option, we normally get fewer K points, but we need to calculate it. So except the hexagonal and the other like 𝗨𝗶𝗱𝗀, triclinic, trigonal lattices, this shift option, reduce the number of K points, what we need to calculate. So our virtual lab people already did some benchmark stuff for us. So normally, except the hexagonal and these guys, you just put the 1 here. Oops, what's happened? What happened? Yeah. Okay, and then yeah, and choose number of cores and your job name. And before submitting your job, you can also save your job here, save, and then submit your job. Check the status. After finishing your job, you have to check your structure. So click the update and click module connecting to your job. Then you will see this window and click the final structure, and you can see your structure. And you can basically download your structure with different formats. So normally CIF is a kind of standard format, but you can also download your file with different formats. Then check your structure using different software like Vesta. And then we will do band structure calculations. This is the flow chart. You should provide your structure and do SDF, self-consistent calculation here. And you will generate the electron density and then calculate the band structure and those calculations. So the reason why we need to calculate those calculations is that to project your orbital into the band structure, we have to calculate the density of state for each orbital. That's why we need a those calculation here. Yeah, it's the same. Go to the simulation and DFT Quantum Espresso. And you can also connect to the previous your calculation. because the previous one already include the all information that we need. And let's see, why is it so slow? Okay, yeah, select the band structure in data to get, for band structure calculation, we have to select the this point. So here we're gonna look at the eigenvalues from m to gamma via r. So you can just choose m, r, gamma. And first of all, you should select your crystal system. Our system is cube. And second, you have to choose like number of k points between 2 points. So let's do 10 points between m and r, 10 points between r and gamma. Also, well, this platform actually will provides the default the pathway, but in this case we don't follow the default pathway and delete the default pathway and click the this pathway. Just click M, R, gamma, and then you have to change the last digit with change to the 1. So first 3 digits means the corresponds to the coordinate in the reciprocal space, and last number is the number of k points between these 2 points. So we don't need just 1 point at the last point. We have to change to 1. And add those steps for orbital resolve band structure, and you'd better reduce the number of cores because those and band structure calculations is very small calculation. So let's do 8 or 16, whatever, and start your job. And after finishing your job, go to the analyzer, quantum espresso, band structure, and connecting to your previous work. Click the band, and you will see band here. And then we need to project our density of state into the band structure. So please click this plug-like shape and connecting to our previous calculation and click the projected. Then you will see this beautiful columns and row, and you can choose the atoms what you want to see. So in this case, I click the lead one and iodine 2 and choose the s orbital, p orbital, here s and p. Then you will see the orbital projected band structure in here. You can also download the image. So yeah, so look at the this band structure. We can see that this balance band maximum is the orbital is a mix between lead 6 and iodine 5p, which is in good agreement with my previous paper, and also conduction band is also shows the good agreement with my previous calculation. So thank you for your attention. This is last slide, and let's move on to the real tutorial session.